All right, we are covering 8.2 trig form of complex numbers in this video. Short one. Take notes, check in for attendance. 8.2 trig form for complex numbers. Okay, so what we're going to do here in this section, we're going to take a look at absolute value of complex numbers. We're going to take a look at the conjugate. We're going to take a look at trig form. And we're going to take a look at trig form to standard form. All right, so let's start with graphing complex numbers. Okay, so let's start by looking at that. So let's take a look at graphing a plus bi. Okay, so what happens is when we're graphing this complex number, what happens is we need two axes, one to represent the real part. So that would be this horizontal one. Okay, so this is the real axis. And this one here would be the imaginary. Okay, and maybe I want to graph something like this. Let's graph 3 minus 2i. Okay, then that means I would have to go 3 on the real, 1, 2, 3, and negative 2 on the imaginary. So right here, so it's like this vector that goes out to the point 3, negative 2. Okay, so this here is how you would graph the complex number a plus bi. Okay, so why don't you try these? Go ahead and graph the following points. Go ahead and you can label them A, B, C, D. And so that way it doesn't get too crowded on the grid. All right, so go ahead and graph point A, negative 3 minus 4i. Point B, negative I. Point C, which is just 7. And point D, which is 2i. Okay. All right, so I'm going to go ahead and draw this here, but you can go ahead and hit the pause button. Okay, so negative 3 minus 4i. So that's going negative 3, 1, 2, 3, and then negative 4, 2, 3, 4. So right here, this would be, I can't get my lines straight. Okay. Here we go. So this is point A, or this is a complex number A. All right, and then negative I, that would be here. So I is right over here. This is complex number B. C, so 7 on the real. So that's 1, 2, 3, 4, 5, 6, 7. So that's right there. Okay. Here, let me give some color so you can see some of these. B is this one right here. C is this one over here. And then D is 2I. So 2I, 2 on the imaginary. Right over here. Let's do that one in green. Okay, so these are the 4 complex numbers. So you can see here it's very similar to just plotting this point, -3, -4. And over here, since the real part is 0, this is like saying 0, -1. And here, the imaginary part is 0. And then here, again, the real part is 0. The imaginary part is 2. Okay, so very straightforward for graphing. All right, let's take a look at the absolute value. The absolute value of a complex number has also another name. It's called the modulus. So you might see in the directions in the homework, it'll say find the modulus of this complex number. Okay, it's the same as the absolute value. And absolute value means the same thing with complex numbers as it does with real numbers. When we talk about real numbers, right, you don't have to copy this part, right? When we're talking about like the absolute value of 3, or if we're talking about the absolute value of -4, they mean the same thing. We're saying, okay, well, like how far is it away from 0, right? How far away is it from 0? And so that this idea of absolute value being the distance away to 0 transfers over here to complex numbers. So if we look at this complex number A, then we want to know how far is this to the origin 0, 0. Okay. And so that's where the distance formula comes in. So here, if z is a complex number, x plus yi, right? Then the absolute value of z is going to be the square root x squared plus y squared. Okay? Because that's the distance formula, which comes from the Pythagorean theorem. Okay? All right, so let's take a look at these examples here. Find the modulus of each. So again, modulus is just absolute value. Find the modulus of each. And we're going to be using this formula right above here. Okay, so A, suppose your complex number is 4i. B, suppose your complex number is 6. And C, suppose your complex number is 1 plus 3i. Okay, so we have the 3 different situations. One where the real part is 0. Second example where the imaginary part is 0. And the third example where neither parts are 0. Okay. All right. So we just follow this here. So the I'll do A over here. Absolute value or modulus of z is going to be the square root of, so here it would be 0 squared plus 4 squared. So that's just going to be 16. So that would be 4. Okay. For B, the modulus of z is going to be 6 squared plus 0 squared. So that's going to be 36. Square root 36, which is 6. And then C, the modulus of z, is going to be 1 squared plus 3 squared. That's going to be 1 plus 9, which is square root 10. Okay? All right, so that's the modulus. And let's take a look at something called the argument of z. Okay, so the argument and we use this notation, argz. Okay. And so the argument of z The argument of z is the smallest. So keep that in mind. It's the smallest positive angle. Smallest positive angle theta from the positive real axis to the graph of z. Okay, and I'll draw you a visual. So here, if you have your real number, let's say your complex number, z over here, which is some x plus yi, right? Then that angle, that argument of z, would be this angle right over here. Okay? So theta here is your arg z. So it's basically the angle the angle of that complex number, kind of like when we were doing the angle of vectors. Okay. All right, so that now leads me to the trig form of complex numbers. Okay, so trig form of complex numbers. Okay, so I'm going to go ahead and draw that again over here, but I'm going to label it a little bit more than I have it labeled up there. All right, so we have this trig, we have this complex number over here, right? So I'm going to call it x plus yi. All right, and this has some distance r. And we know this is some distance x, and this is some distance y, and here's the argument of z, right? Okay, so we know from trigonometry that cosine theta equals x over r, adjacent over hypotenuse. And we also know that sine theta is opposite y over hypotenuse, which is r, right? Now, if I take both of these equations, right, if I take this one here and solve for x, I can multiply both sides by r, and I get r cosine theta equals x. And over here, if I do the same thing with this equation, solve for y, multiply both sides by r, I get r sine theta equals y. Okay, so here I have values for x and for y. Okay, so it turns out that if z is a complex number equal to x plus yi, then the trig form of z is given by, well, so if this is our standard form of our complex number, z equals x plus yi, x and y are some real numbers, right? So if this is our standard form, then the trig form of this complex number would be to replace the x and y with these trig expressions over here. So instead of x, I'm going to use r cosine theta, and instead of y, I'm going to use r sine theta. So z equals r cosine theta plus I sine theta. Okay. Oops, r here. R sine theta I. Okay. Another way to write this is if we have r factored out here, cosine theta, and then we also put the I in front of the sign just to make sure that it's understood that we're not taking the sign of an imaginary value. Okay, so this here is the trig form of a complex number. Uh, your book uses also a third way of writing it, which is completely new to me over the 27 years of teaching this. So they use this C for cosine, I for the imaginary, and S for sine, and they just write it like this. Okay, so just be aware of that if you see that in the homework. So this is your trig form of a complex number, and we'll look at some examples here. Keep in mind that here in the drawing, in this graph here, that R is the absolute value of Z and theta is the argument of Z. Okay? All right. So let's take a look at a standard form of a complex number, and let's rewrite it in trig form. So here, suppose we want to write this complex number, Z, which is equal to 1 plus I square root 3 in trig form. So let's rewrite this in trig form. Okay, so again, always helpful to have your complex number graphed. Okay, so here we go. There's 1, and square root 3 is somewhere between 1 and 2. Okay, so here's our complex number Z. All right. We know that this is square root 3. We know this is 1. Okay, so we can go ahead and find R. R is just square root of 3. R squared is square root 3 squared plus 1 squared. So R squared is 3 plus 1. So R squared equals 4. So R equals square root of 4, which is 2. Okay. All right, so we have all three sides. All right, so in order to write this in trig form, we need to replace the x with a trig function and the y with a trig function. So we know that x is r cosine theta, right? And y is r sine theta. We don't know what theta is. Okay, so we can do tangent inverse of y over x, right? Will give us our theta. So tangent inverse of square root 3 over 1. We have this one memorized. This is one of the ones we memorized. We know this is going to be 60 degrees. Okay? And really, we only need these two things right here. We need r and theta to write the complex number in trig form. Because remember, it's r cosine theta plus I sine theta. Okay? So we only need to replace the r and the thetas with what we find. Okay? So then our final answer is going to be 2 times cosine 60 plus I sine 60. And that's it. Okay? So you only need to find r and theta, and you can write the trig form. Okay, that new way of writing it would be 2CIS60. Okay, 2CIS60. All right. So when they ask you, okay, write this in trig form, you're going to have to draw this out, come up with R and theta, and you're done. Okay? R and theta, and you're done. All right, let's go the reverse. The reverse is much easier. The reverse, let's go ahead and write Z, which equals 3 cis 45 in standard form. So when you have to write it in standard form, all you do is work out the trig, either in your head or by calculator. So C equals 3 cis 45 degrees. That's the same thing as saying 3 cosine 45 plus 3 sine 45 I, right? Okay, so what's cosine 45? Well, that's going to be square root 2 over 2. What's sine of 45? Oh, it's also square root 2 over 2. Okay, so that here we would get 3 square root 2 over 2 plus 3 square root 2 over 2i. Okay, so you just work out the trig. If you don't have it memorized, if it's an angle that we don't have memorized, then you would just use your calculator. Okay, so that's it. Being able to write the trig form of a complex number, that's kind of the main thing. So being able to do this part right here. So again, you just need to find R and theta, and you just use the distance formula, which comes from Pythagorean, and you use your tangent inverse. Okay, because you're given y and x. All right, if you have any questions, make sure you text me or email me.